All right, last night we gave you an introduction to imaginary numbers. We defined that I was equal to the square root of -1 by definition. That's not something we created, that's just something we took for granted. And we talked about how to simplify radicals like -36, and we tried to explain why the answer was 6i. So 6 times I created a new set of numbers called imaginaries. And tonight we're going to take it one step further. We're going to create an even greater set called complex numbers. And really, believe it or not, every number that you've ever worked with since you first came to school in kindergarten or pre-K was really a complex number. They fell within the set of complex numbers. We just didn't know it at the time. So basically what number one's saying here is all numbers fall into a very broad category known as complex numbers. Every number you've ever worked with was actually a complex number. Now, complex numbers can always be thought of as a combination of a real number, which is the part you've been working with an imaginary number, which is the numbers you just learned about yesterday. And they'll have the form a plus bi. So a plus bi is a complex number in generic form, where both a and b are real numbers. Now, we say that a is the real part of the number, and we say that bi is the imaginary part of the number. All right, and on the next slide, I'm going to try to explain why all the numbers you've ever worked with were actually complex numbers. We just didn't have the bi part to our complex numbers all. Okay, so here's a Venn diagram that does a pretty good job of visually explaining the subsets of and which kind of numbers fall within other sets and so forth. But just the best example I can give you, if you think of whole numbers here, whole numbers start with the number 0, 0, 1, 2, 3, so forth. All right. Now, every whole number is an integer, but not every integer is a whole number. Does that make sense? It's kind of a weird saying. But so just what are integers? Well, integers start with like negative and infinity, and they get negative. They come to -1, -2, -1, 0, 1, 2, 3, and so forth. So you'll see that the difference is whole numbers start with the number 0. They don't go anything below 0. So you'll notice every whole number is an integer, but not every integer is a whole number. So the same thing applies to our big set here. For instance, every rational number is a real number, but not every real number is rational. For instance, rational numbers are basically numbers that can be expressed in terms of a fraction. Okay, like 1/3 is a good example of a rational number. Even though 1/3 is an endless repeating decimal, it's still rational. Now, irrational are things like radical 5 that are endless decimals without a repeating nature. Or maybe pi is a good example. And later on, we're going to introduce you to a letter E that actually represents a number that's irrational. But anyway, all complex numbers and all the numbers you've ever known fall within the bigger realm of complex numbers. All right, as a way of just kind of easing into it and stuff, we're going to just introduce you to a very simple concept of graphing complex numbers. And since each complex number has two components, what are those components? It's the A component and then the BI component, or otherwise known as the real component and the imaginary component. Now, every time I say real, I want you to think of the A, and every time I say imaginary, I want you to think of the BI part of it. Anyway, because there's two components, they must be plotted in a two-dimensional system. Now, this two-dimensional system is actually a lot easier than it sounds. It's got a few weird names, though. And those weird names, sometimes we call it a complex plane. And here's the really weird name. Sometimes we call it an argon plane. And you're maybe going to hear me use that word, maybe 2 or 3 times the rest of the year. But there's, there is that small chance that the Regents exam will refer to it as such. I've never seen them do it before, but I want to expose you to that name just in case. So basically, what we've got cooking here is the x-axis represents the real coordinate system, and the y-axis represents the imaginary system. So when they want me to graph A plus BI, I'm going to start at the origin, I'm going to go to the right A units, I'm then going to go up B units, I'm going to put a dot right there at the tip top, and then I'm going to draw what's called a vector that originates at the origin and extends to the dot that I just plotted. So what this ray right here and that's how I'll describe it as array, is called a vector. And whether you've had any physics experience or not is irrelevant. You're going to be okay, and that vector is just a fancy name for that ray. So we're going to start off with some real easy examples, and I imported a nice Venn diagram here to get us started. So maybe the directions wanted us to graph a few complex numbers, and the first number maybe was 3 plus 4i. So I would say to myself that the a component, or the real component, is 3 units, and the imaginary component is 4. So what I would do is I would start at the origin, I would walk to the right 3 units, and then I would walk up 4 units, and you'll notice how they did put a dot there already, and they drew a nice vector extending to that one, so that one's already in pink. Number 2, maybe they wanted me to do negative 4 plus 2i as a complex number. Well, the real component is negative 4, the imaginary component is a positive 2, so what I'm going to do is I'm going to start at the origin, I'm going to walk to the left 4 units, I'm going to walk up 2 units, put a nice dot right there, and then start at the origin and extend a ray or a vector to that dot. And then you'll notice there's a few others. There's a few squirrely ones. Like sometimes they may just say, hey, I want you to graph 4i. Now believe it or not, that's still a complex number. It's just that the a component, or the real component, is a 0, and then the b component is 4. So you wouldn't walk left or right at all. You would simply just start at the origin, and you would go straight up 4 units, and there would be your ray. The other squirrely one that you might see is just the good old number 3. And again, that's still a complex number, and this is where I'm trying to convince you that every number you've ever worked with since kindergarten was a complex number. The a component is 3, but what's the b component? Yeah, it's actually a 0 because there is no second component, or there's no I in that term. So we would walk to the right 3 units, we would not go up or down, and we would just we would keep our ray or our vector right on the x-axis. Alright, so here's a bunch more. We're going to practice graphing. So grab one of your sticky pads and slap it in your notebook here. Then the first thing I want you to do is I want you to draw your axes right down the center of that notepad, that sticky, and I want you to label the x-axis as a reals and the y-axis as imaginaries. That's very, very important that we get those axes labeled here on these new problems. Now for the first problem, for letter A here, the real component is a 5, and the imaginary component is a negative 2. Oops, I forgot my B equals. Okay, and so what I'm going to do is I'm going to start at the origin. I'm going to walk to the right 5 units, 1, 2, 3, 4, 5, and then I'm going to go straight down 2 units, and right there is my dot, and then I'm going to draw a vector, and bingo, there's my answer. Alright, for part B, my real component is a 3, so I'm going right 3, and then my imaginary component is a 7. So I'm going to go to the right 1, 2, 3, and then I'm going to go up 1, 2, 3, 4, 5, 6, 7. Okay, bingo, right there. I'm going to just extend a ray from the origin up to that point, and that's my second answer. Alright, let's go a little bit faster here if you're feeling more comfortable. For part C, I'm going to walk left 2, up 6. Left 2, 1, 2, 3, 4, 5, 6, and I've got array right there. Now just to review our quadrants really quickly, this blue one is in quadrant 2, the red one was in quadrant 1. So always start in the upper right hand corner is quadrant 1, then we're going to go counterclockwise, and then 3 would be down here and 4 would be down here. So just a little review of the quadrants. Alright, let's bust out another color here. D, I'm going to walk left 4 units. 1, 2, 3, 4, and then straight down 1 unit is all. Because that coefficient right there, that's a b value of negative 1. Alright, what makes E a little bit trickier? What makes E a little feisty? Well, what you've got is a real component of 0 and a b component of 5. So I'm not going to go left or right. I'm just going to go straight up 5 units and draw a vector that sits right on the y-axis there. And the last one, what makes F a little tricky? Well, what makes F a little trickier is that the A component's negative 6, but the B component is a 0 because there is no I in the problem. So all I'm going to do is I'm going to go straight left 6 units, and I'm not going to go up or down, so I'm going to stay right on the x-axis, and there's going to be my last vector. Here's a very typical region style question, and they're going to ask if we did graph the complex number negative 3 plus 5i, what quadrant would it fall in? So just review, our quadrants are 1, 2 here, 3 here, we're just going counterclockwise. And the x-axis represents all of our real numbers. Our y-axis represents all of our imaginary numbers, so we've kind of set the stage, so to speak. Now, when I was looking at that complex number, the real component was -3. The imaginary component was a +5, so I'm going to go left 3, and then I'm going to go up 5 units, 3, 4, 5, and I'm going to say my ray, or my vector, falls right there in quadrant 2. Winner, winner, chicken dinner. All right, real quick recap of what we've covered so far. The generic form of a complex number is a plus bi, where a represents the real component and b represents the imaginary component. And if we wanted to graph it, we would start at the origin, we would go to the right a units, and we would go up b units, and we would come up with a vector that looked something like this. Now the next question is we want to find the size, or sometimes we'll use the word length or modulus even. That's even a funny word, but that all means modulus just means length, or which means size. All of these words are synonymous with each other. So we're trying to find the length of this complex number. In other words, what we're trying to do is we're trying to figure out how long is this ray right there? How long is it? So I'm going to put a little question mark there. And that's what we're trying to figure out. So what we're going to do is we're going to create a right triangle here. And I'm going to say, well, I started at the origin and I went to the right a units and then I went up b units, and maybe we'll say the hypotenuse is c. So we could say, well, according to the Pythagorean theorem, a squared plus b squared equals c squared, and if you want to find the length of side c, we're going to just take the square root of both sides, and we'll say that length of c is radical a squared plus b squared. And that's all we're going to do here today, is we're just going to use that Pythagorean theorem. We're going to say that c represents the length of my vector, and it's always going to be radical a squared plus b squared. Alright, so here's 3 examples, and I want you to say to yourself right away, as soon as they ask you what the size of a complex number is, or maybe the length or the modulus of a complex number, tell yourself we're going to use the formula c equals radical a squared plus b squared, where a represents the real component and b represents the imaginary component. So as I look at letter A here, the real component is a 3 and the imaginary component is a -4. The negative, actually, believe it or not, turns out to be irrelevant, because by the time we square it, we're guaranteed to be positive. So I'm just going to type, I've got radical 3 squared plus -b squared. And let's see, that turns out to be 9 plus 16, which is radical 25. My final answer is 5. That complex number has a length of 5 units. All right, part B. The real component is 12, the imaginary component is 5, and the length is going to be 12 squared plus 5 squared. So we've got radical 144 plus 25. Wowzers, I think we're going to get another friendly number here. Can you believe it? 169, and the radical 169 is 13. So 13 units is the length of that complex number. All right, let's break out one more color here. All right, last one. My a value is a -4. My b value is a 2, so I'm thinking, let's see, -4 squared is 16, plus 2 squared is 4. I've got radical 20, and of course I want to simplify it, so I'm thinking radical 4 times radical 5, which gives me 2 radical 5 is the length of that complex number. All right, we've got ourselves a 3-part question, and we got our complex number, 3 plus 6i. And first of all, let's go ahead and plot it. We're going to go left 3 units and up 6 units. Notice we do have the axes already labeled here, so make sure you've got the same in your notebook. And if we go left 3, up 1, 2, 3, 4, 5, 6, that's going to put me right there, I believe. We're going to draw our nice vector, or array, starting at the origin. And we did land in quadrant 2, just to review our quadrants. Okay, so we checked off A. Part B says find the modulus, and all I want you to do is think size. That's the size of a vector, or its length. So we're going to use c equals radical a squared plus b squared, which in this case is going to be -3 squared plus 6 squared. And let's see, 9 plus 36, and that's radical what, 45? And radical 45 can be simplified into radical 9 times radical 5, so my final answer there is 3 radical 5. Now the last thing they wanted us to do is try to explain. And they said, what distance does this modulus represent on the graph? So I would say it's the length of our vector, would be one way to describe it. Or you could say, you know, it's the distance from the origin to the tip of the ray, or the end of the ray. Okay, the couple ways to describe it, and all it is I'm going to draw a little squiggly bracket right there to represent the length, and that is your 3 radical 5 length. Okay, I wanted to sneak in an example here in between, and I want to ask you, what's the absolute value of 4 plus 5i? Now, asking for the absolute value of a complex number is the exact same thing as what we've been doing. All it is we're measuring length or size, okay? And that's really what all absolute value was since day one. You know, when back in the day, if we asked you for the absolute value of -5, what we're asking you for is the distance between -5 and 0 on a number line. That's all it was we were measuring distance. And that's why we said the answer was +5, because the distance from -5 to 0 was 5 units long. So again, when we want the distance or the length of 4 plus 5i, we're going to go ahead and use the formula we just used. And the point of this example is to drive home the fact that it is the same, indeed the same question. And so we're going to end up with about radical 41 for this length. So absolute value is length. And believe it or not, you could actually plug this entire problem into your calculator if you know where the absolute values are, and that's in the math menu. So don't be afraid to do that on a multiple choice question. Just plug it into your calculator. Okay, our last mini topic for tonight is we're going to talk about adding and subtracting complex numbers. And this is a breeze. This is actually a walk in the park. And it's very similar to how you would add or subtract any binomials you've ever seen. The name of the game is focusing on like terms. Okay? If you can identify like terms and so forth, you're going to be in good shape. In other words, basically you want to combine the reals with the reals and combine the imaginaries with the imaginaries, and that's the bottom line. So when I look at the first example here, -2 and 6 are my reals, and if I combine those I'll get 4. And then 7i and 2i are my imaginaries, and if I combine those I'll get 9i, and you're done. That's all there is to it. The second one, part B, combine your reals with your reals and you'll get 20. Combine your imaginary with your imaginary and you'll get positive 3i. And boom, you are done. Just make sure that you notice that that second one was a -1i. Alright, third one, let's combine the 5. You know what? Let's do this first. Let's go ahead and distribute that negative. So this is really 5 plus 3i minus 2 plus 7i. Now we'll combine like terms, combine the 5 with the -2 and get a 3. And then we'll combine the 3i with the 7i for a total of 10i. Alright, so all we're doing is combining like terms. Pretty straightforward. Again, on part D, let's go ahead and distribute first. Anytime you see that minus sign, I really want to focus on distributing. So we got -3 plus 5i plus 8 minus 2i. Combine the -3 with the positive 8 and you'll end up with 5. And then combine the 5i with the -2i and you'll have a grand total of 3i as the difference of those two complex numbers. Alright, here's a real straightforward multiple choice question. They want the sum of these two complex numbers, and then they want to know in which quadrant would the sum fall within. So combine your like terms. I'm going to get -2 minus 3i for a sum. If I graphed that complex number, I would go left 2 and then down 3 units. That would put me definitely in the third quadrant. So before I turn you loose tonight and let you try this last problem on your own, let's ask ourselves, let's kind of, what did we learn tonight? We introduced you to the idea of a complex number, and I tried to convince you that every number you've ever worked with since kindergarten was actually a complex number. A complex number is a combination of a real number joined together with an imaginary number. It's the joint sum or difference of a real and an imaginary. We talked a lot about graphing. And we came up with this new complex plane, sometimes called an argon plane. And after we got done graphing, we talked about how to find the length or the size or the modulus of a complex number. And we discussed how that's the same thing as doing the absolute value of a complex number. And then the last thing we finished with tonight was adding and subtracting complex numbers. And the name of the game there was simply focusing on like terms. And if you could find the like terms and combine them accurately, you're going to be in great shape. And hopefully we proved that that was a walk in the park. So good luck. Of course, exercise number 7 is all yours. That'll be the first one we check in your notebook tomorrow. So good luck, and we'll see you.